Hello students, welcome to Inside Physics. In this session, we are going to discuss about angular velocity. This is concerned with the lesson rotatory motion. So, angular velocity is very important considering and understanding the rotatory motion. So, there is a difference between circulatory motion and rotatory motion. If you consider a particle rotating about an axis, so that is called a circular motion. So, when you consider a particle, single particle which is rotating about an axis, then that single particle is supposed to make a circular motion. So, when you consider a system of particles that moving in circles around a fixed axis of rotation, then those system of particles are supposed to have rotation. So this is the difference between circulation and rotation. Now we understand the importance of angular velocity in rotatory motion and its relation with linear velocity. The concept of linear velocity we have seen in the previous sessions, that it represents the direction and magnitude of a particle in linear motion, that means straight line motion. Here it is rotatory motion. So the angular velocity is represents with a particle or system of particles. It actually is along the axis of rotation. That means, see, if we consider an object with irregular shape, this object may have so many particles here, and we have an axis of rotation like this. This axis of rotation is about on which all the particles will rotate. So these are all the particles you may consider as molecules inside an object which is of this kind of an irregular shape. So the angular velocity will always be along the axis of rotation, and when you draw a circle of rotation for this particle, the linear velocity of this particle will be along this circle. When you draw a tangent at this point, the linear velocity will be like this, and we need to show exactly into the board here, not in this direction. You can imagine when this is the circle of rotation, at every point on the circle the linear velocity v bar is along the tangent at that particular point. If you take this point here, it may look like this, and if you take a point here, you may need to draw like this. This is the circle of rotation, and the radius vector, this is called the position vector, from which we take a point on the axis of rotation, and the distance between the velocity vector and the point we have taken on the axis of rotation. If this is the point we have taken, that is the position. This gives the position vector. So in this way we understand the linear velocity and what angular velocity. What is the importance of angular velocity in rotation? Just like we know the definition for linear velocity, the average velocity is equal to total displacement by total time. This is the average velocity definition we know from straight line motion, and here the instantaneous linear velocity will be rate of change of displacement. So in the same way, angular velocity is also defined as the angular velocity is always represented with the Greek letter omega, and the angular displacement, here it is linear displacement. Now in rotatory motion we consider angular displacement. What is angular displacement? When you draw a circle and an object has moved from A to B, and the line drawn from the point A to the center and the line drawn from the point B to the center, this is the arc length. AB is the arc length and this is called arc of the circle. This arc will subtend an angle theta at the center. So this is the angular displacement. Theta is the angular displacement. So here omega, the angular velocity, that means if you take the average angular velocity, we can write this, the angular displacement by time, theta by t. That means total angular displacement by total time. If you consider the instantaneous angular velocity, that means rate of change of angular displacement, that means this can also be taken as a very small interval of time. So the time interval will goes on decreasing and it should not be 0 but it almost tends to 0. So that is the definition of instantaneous velocity. We have all seen in the previous sessions what is instantaneous velocity and what is average velocity. So this is angular velocity, and if you take a point here, the initial point and the final point where the object is moving from A to B, you consider a point P, the linear velocity will be along the tangent as I already told you, right? And the position vector from 0, that means the center of the circle to this point will represent the position vector. Okay, here the linear velocity is a vector which has both magnitude and direction. Here the direction of the linear velocity will be changing from point to point but not the magnitude in rotatory motion. Here the angular velocity will be along the axis of rotation. If this is the axis which is perpendicular to this board and the object is rotating like this, it can rotate in clockwise or anti-clockwise. You may consider any direction, both are called the rotatory motions. So here the angular velocity is considered to be a vector quantity, but it appears to be a scalar, but we will not justify it, but we must accept that the angular velocity is a vector because it is along the axis of rotation. So what is the relation between angular velocity and linear velocity? How to get the relation between linear velocity and angular velocity? So we know that V is equal to rate of change of displacement. The instantaneous velocity is nothing but rate of change of displacement, and I will multiply numerator and denominator with d theta, that means angular displacement, ds by dt, ds by d theta, and here I will also take like this. So we all know that from the properties of circle that arc length by see the theta here is given by arc length by radius, right? This is we got from properties of circles. That means this is the angle theta subtended by this arc. The arc length by its radius gives the angle, that is the properties of circles. From this we can write radius is equal to arc length by theta, that means angle, arc length by angle. So here we know that ds by d theta, small displacement, that means if you take a small arc length here, that small arc length ds will substitute a small angle d theta, that means ds by d theta will give you the radius of the circle. So d theta by dt, We know that from this relation d theta by dt is nothing but instantaneous angular velocity. So here this is a vector, this is a position vector, this is also a vector, angular velocity. So here we can take the cross product of these two vectors, so to get another vector. Vector multiplication is done in cross product so that to get another vector. If you want to get a scalar, what you will do? Generally, if two vectors are multiplied, means it may be either in dot product or it can be done in cross product. The resultant is a vector, we must take the cross product. So here this is the relation. So what are the angles between these three vectors? We know that position vector is always perpendicular to the linear velocity. We will represent in a much bigger diagram to understand it better. So we have a circle here. So this is the position, and r bar, that means the position vector from here to the point. This can be called as the center of the circle, and the linear velocity is always along the tangent. We already discussed. So these two are perpendicular, right? And r bar and v bar are perpendicular to each other, and the angular velocity, here you see angular velocity, as I already told you, is along the axis of rotation. So these three vectors v bar, r bar and omega bar along the axis of rotation are three mutually perpendicular vectors. Then r bar cross omega bar gives, this is nothing but r omega, because this is equal to r omega sin theta. As we know, this is equal to r omega sin theta. Theta becomes 90, then sin 90 is 1. So the magnitude of linear velocity is nothing but radius into angular velocity. So this is the magnitude of the linear velocity. So here one point we must remember is the angular velocity of each and every particle of a rotating object is same. When you consider this as a sphere, consider this as a sphere like a ball, like a football or cricket ball which is spinning, then each particle, you may consider so many particles in this sphere or ball, so they are rotating like this, and consider this as an axis of rotation. This as an axis of rotation, and the ball is rotating like this. So all the particles along this axis, besides and either way, both sides, each particle moves with the same angular velocity. That is the point we must remember. So all the points, this rotates in this circle, this rotates in this circle. See, this point will be rotating in this circle. So this may rotate in this. These are the circles, and this is the axis of rotation. So the linear velocity is multiplied with angular velocity and the radius. So radius will change for each particle. This is the radius of the circle of rotation for this particle, and this may be another circle. This is a very small circle just besides the axis of rotation. This is the radius vector. So the radius will change from particle to particle, but the angular velocity is same. That means from this relation, the angular velocity is constant, we can choose this relation as v proportional to r, because angular velocity is constant. So linear velocity is directly proportional to radius vector, radius of the circular rotatory circle in which the particle is rotating. If the radius is more, it moves with more linear velocity, but remember the angular velocity is always same. If it is rotating in a small circle, the linear velocity is also less according to this relation. The linear velocity is directly proportional to radius of the circle in rotatory motion. So these are the points we must remember. And here, see, if you take any other point as origin and draw a position vector, how that this relation will be coming in a case where if we take any other point as origin and we consider this as a position vector. This is a position vector. Okay. So OP, I have taken the origin instead of here, I have taken here and try to get a relation between linear velocity and angular velocity. We will try to do it. See, here V is equal to R omega, right? So R means I have taken this OP. That means we can take a cross product of this. So OP cross angular velocity is a vector. This is also a vector. This is also a vector. Linear velocity is also a vector. OP here we can write as sum of OC and CP, right? OC plus CP cross omega bar. Okay, so see, if you consider this OC bar cross omega bar plus CP bar cross omega bar, because the cross product is distributive, OC, see this is the angular velocity and the point, see this one, this is along this axis of rotation, and CP, in all the points on this axis of rotation does not have any angular velocity. So what happens? This will become 0 plus Cp bar. Cp means this is radius only. Radius, you know why it has become 0? See here the angular velocity on this line for a particular particle is 0. So that is why it has become 0, and now we derive this like as R bar cross omega bar, and R and omega are always perpendicular. That means it can be written as R omega sin theta, and we get a relation between linear and velocity and angular velocity as like this. So in both cases, even if you take a point at the center or any point as origin on the axis of rotation, the relation between these two is coming like V is equal to R omega. For more general rotation, we can imagine, we can assume that the angular velocity, the direction and magnitude both will change. But for a normal rotation in which the axis of rotation is not moving, we only say the magnitude is constant, the direction is also constant. But for a more general relation, the magnitude and direction may change in a what you call a more general rotation, like a spinning top, like that. Okay, this relation is also useful for the rotations like precision, where the axis of rotation is fixed at some point, like you can see it in a spinning top, and the top will be having the axis of rotation is also spinning. You can see it is in when you spin a top on the floor. At the time of the ending, it may take a movement of precision, that is called precision, with the axis of rotation fixed at one point. So this is all about angular velocity and its relation with linear velocity. This concept has a very importance, high importance in the coming topics in rotatory motion. So we will take up the important other topics in next session.